Hello everyone and welcome to the NPTEL course in Pharmacognosy and Phytochemistry. Welcome to another week of learning beautiful natural set of compounds. Now, whenever you take a walk along the garden, sometimes you see very beautiful flowers. Now these flowers carry vivid colors and sometimes these colors astonish you and make you think what exactly does the nature do to bring about such a vivid plethora of colors that are there in the plants. How do they appear and what are they? So this week we are going to dwell into set of compounds called as flavonoids, which also contributes to some of these natural pigments. So what are they? Let us study little bit in detail. So flavonoids by their chemical nature are carbon 15 compounds, that is they possess 15 carbon compounds, and this 15 carbon compounds can be broken into set of 3, that is C6, C3 and C6. How do you break this? So this is the first C6, then you have the C3 and the next one is C6. So together you can call them as C6, C3, C6 compounds which occur in nature. Now if you see them in nature, they are always hydroxylated, that means they carry polyhydroxy groups across the rings, and that is why they are polyphenolic in nature. So flavonoids can be defined as polyphenolic compounds having 15 carbons and carrying what is called as typically a benzopyran nucleus. To this benzopyran nucleus is a phenyl ring substituted, so chemically they are phenyl benzopyran compounds. Now owing to their hydroxyl substitution, so imagine lot of hydroxys being attached in some cases at different positions, and as they are polyhydroxyphenolic compounds, this hydroxyl groups render them very polar in nature, and as a result you will find they have a very good solubility in alcohol, that is mid-polar solvents, because the phenyl rings bring their hydrophilicity towards a little mid-polar region, but the hydroxy groups attribute to their polar nature. So flavonoids are soluble in alcohol. On heating they dissolve, or they are soluble in water as well, but on cooling they tend to precipitate out sometimes. So depending upon their molecular weight, depending upon their nature, some of the flavonoid derivatives will be soluble or more soluble in alcohol, some of the flavonoid derivatives would be more soluble in water. Now they are present in different plant species, but the most common ones is Leguminosae or the Fabaceae family, Polygonaceae family and the Rosaceae family. Many of the flower petals that you see that in the garden also attribute their color to this beautiful set of pigments. Flava naturally means yellow, and most of the flavonoid derivative are off white to yellow in color, bearing anthocyanins which have a vivid color palette. Now in terms of their occurrence, flavonoids have a little kind of UV protective activity, and as a result you will find them located on the leaves or different flower petals. So when they are located in the leaves, if you see the upper epidermis of the leaves, it is coated with waxy material to prevent it from absorbing water. So when these flavonoids are there in the upper layer, they are mostly euglycones like we studied, do not have sugars, but when they are located in the mesophyll or the internal regions, they are generally more polar, and many of these hydroxyl groups are then substituted by sugar. So you will have flavonoid glycosides in the sap region or in the mesophyll region, whereas in the outer coat or the lipophilic region you will have more of this euglycones occurring. Now there's a plant called as Sophora japonica, and if you see the flower buds of this plant, they have as high as 15 to 20% of flavonoid called as rutin. Now, what functions they serve in plant? Now, flavonoids are very important to maintain the structural integrity of plants. Some of these plants also use flavonoids as a kind of messengers. They are used in signaling or communication with adjacent plants. Not only with adjacent plants, they also use it as a mode to communicate with insects, microbes. Now this mode can be used as a very easy way to, in case of color, they can act as attractants. Sometimes these flavonoids form derivatives which can act as insect repellents. Sometimes these polyphenolic derivatives have an antimicrobial activity, that is, they have ability to kill bacteria, fungus and some other microorganisms. In that case, they are categorized as phytoalexins. Now, if you see some leguminous plants where these flavonoids occur, in that especially in the root region or in the underground region, they have an important role to play. That is, they associate with the nitrogen fixing, that is your rhizobacteria species, and form symbiotic associations with them. This is something which helps the plant thrive well. Now, not only that, if you know flavonoids, you must have seen when people advocate green tea or colored fruits, they say that they are antioxidant, free radical scavenging. Yes, because of their polyphenolic nature, your flavonoid and flavonoid derivatives possess what is called as a stress protection activity. They do it especially by scavenging your free radicals by themselves, acting as an antioxidant molecules. So not only are they antioxidant, they have a good ability to form complexes with metal ions. So they chelate metals as well and decrease the toxicity of metals in us. Not only are that, if you see carefully, this flavonoids, they have a aromatic ring structure, and this aromatic ring structure absorbs UV. So they act as good UV filters as well for the plants, as well as you will see nowadays in cosmetic applications, some flavonoids have been used for different UV protective effects. Not only that, there are certain classes of flavonoids which we will be studying subsequently. They have phytoestrogen like activity. Now coming to biosynthesis, how are they originated or from where does plant produce it? Now you will see or you will be thinking that whenever a plant is there, it is mostly greenish in color owing to the presence of chlorophyll. But the moment that beautiful flower bud develops, it gets that intense red, blue, purple hues. Now from where does this happen? So in plants we have studied previously, there is a pathway called as shikimic acid pathway, and shikimic acid pathway gives rise to different amino acids. One such amino acid is phenylalanine. This phenylalanine gives rise to a phenylpropanoid nucleus, and if you can see, when I divide this molecule into two parts, your phenylpropanoid can be seen located here. Let me just help you with it. So this is your phenyl, and this is your propane. So here you have carbon number 1, carbon number 2 and carbon number 3. So this is your phenylpropane, and this has its genesis from your shikimic acid pathway. Now coming to this side of chain, especially the A ring part of it. The A ring part of it is unique, that it is found or it is formed by union of C2 building blocks, that is acetyl CoA building blocks. This acetyl CoA form malonyl CoA. This undergoes elimination, and in such a manner you will find 3 acetyl CoA contributing. So this is one acetyl CoA, this is second acetyl CoA, and this is third acetyl-CoA. Now acetyl-CoA you can draw it like this also. So when I want to do it, I can convert it into a ketone, and now you can see of that acetyl-CoA you have 3 hydroxys. So alternating oxygens, and this oxygens later on, or this ketones later on, get reduced to hydroxy. So if you see a typical flavonoid, the substitution pattern remains almost the same. That is, you will see majority of the flavonoids have their hydroxy on 5th position as well as 7th position, and this is because of their biosynthetic origin. So acetyl-CoA condense it in a way that the oxygen is located at 5th and 7th position, and subsequently as you see more and more of this natural flavonoid derivatives, you will reinforce that the hydroxy is typically present at the 5th and the 7th places. So this comes from what is called as acetate pathway. Now you can classify flavonoids depending upon their ring structure. So what we have seen here so far is you could put this as ring A, you could put this as ring B, and then the ring C. The reason the ring C gets a middle position is because eventually ring A is biosynthesized differently, ring B is biosynthesized differently, they fuse, and in the end the ring C is formed. So in terms of numbering, starting from hetero group, you have like this 1, 2, 3, 4, 5, 6, 7, 8, and then your B ring gets 1 dash, 2 dash, and so on. So if you see your flavones now, your flavonoids can be classified depending upon where your B ring joins. So depending upon where your B ring joins, you can have them as flavones, isoflavones, or neoflavones. So again, I'll just write the numbering for you. So 1, 2, 3 and 4 if you remember, and this was your 5, 6, 7, 8. Okay. So if my B ring joins to the C ring at position number 2, I call it as a flavone. If my B ring joins to C ring at position number 3, I call it as isoflavone, and isoflavones are the compounds which have phytoestrogen like activity. Now what happens here is, so typically instead of your 2 or 3, sometimes your ring B joins here at 4th position. So you get a neoflavone. When your ring B joins to ring C via the carbon number 4, you call this compound as neoflavones. Now what happens here is, if you see your flavone and isoflavone, they are typically benzo gamma pyrrone, that is alpha beta gamma pyrrone. But in this case, because the gamma position is substituted by the B ring, your ketone moves here and you get a lactone like structure. So this typically mimics your coumarin structure. You can also classify the flavonoids based on the C ring. So if you remember, this is what we were discussing as the C ring system. So depending upon the C ring, if the C ring is closed to form a pyran, you call it as flavan. Okay. So this is a typical flavonoid nucleus. So this is flavan. In some cases, you will encounter a pyrrone or a ketone out here. Now what happens is, in some cases, especially in flower petals or in the pigments that we were discussing, your oxygen gains an additional valency. So oxygen is generally a divalent, and as you can see here it is shown as a trivalent, and as a result they carry a charge. Now this charge moiety are what is called as a flavinium ion. Flavinium ion is a core of most of the plant pigments, and they are categorized as anthocyanidins. So anthocyanidins are responsible for the different colors of the petals, and they are very unstable. The reason is because they carry a flavinium ion on which the oxygen carries a positive charge. Not only that, because of this charge, if you see your kokum juice for example, you will see on heating or just on keeping it for a day or two, they will quickly polymerize and disintegrate to form brown color adducts. So they are not very stable because of the charge. Now in some cases the C ring totally opens up and you get what are called as chalcones. So here in this case the C ring is not cyclized at all. In that case you will got such derivatives as chalcones. In the fourth case, instead of forming a 6-membered pyrane ring, here you will get a furan kind of ring structure, and such compounds are called as orone. The carbon is there, that is that extra carbon which was making this 6 ring is there, but it has been pushed out of the ring and forms a bridge molecule between your B ring and C ring. Such compounds or such flavonoid derivatives are called as orones. So you have flavonols if the C ring is intact, anthocyanidins if the oxygen carries an additional charge, chalcones if the C ring is open, and orones if the C ring is a 5-membered ring. Now you can also classify the flavonoids based on the nature of substitution. Now observe carefully. Now between, this is your 1, 2, 3, 4. So whenever there is a unsaturation between 2 and 3, you call such compound as flavo. Okay, it is VO, but whenever this unsaturation is removed, these compounds are called as flava. So the name of the flavonoid itself will tell. If I am talking about flavonoids, I should understand that the double bond between 2 and 3 is intact, whereas if I am discussing a flava, that means this bond between the two is gone and a reduction has happened. Now depending upon that, if any alcohol is attached, because the double bond is there, I have flavo, and this all is represented by a flavonol. Okay, and in this case also, if you see carefully, there are biflavonoids, that is 2 flavonoids which are attached to each other, but because there is unsaturation, they are flavonoids. Had it been saturated, it would have been called as biflavanone derivatives. Now you can also classify the flavonoids based on the sugars being present. Now this is similar to glycosides. So if the linkage is a oxygen group, you call it as flavonoid O glycosides. If the linkage is a carbon group, you call it as a flavonoid C glycosides. A rutein is a classical example of a flavonoid O glycosides, whereas Vitexin is an example of flavonoid C glycosides. So if your buckwheat is a common source of your rutein, whereas if you see your Vitex, it's a common source of your Vitexin. Now here mostly one more thing you will additionally observe is, like we said, the hydroxys group are present on 7, 5 and 3 most commonly. And as a result, if you see O glycosides, the O glycosidation will happen when I am talking about ring A and ring C on 3, 5, 7 group, whereas if I am talking about ring B, mostly it will happen on the 3' and the 4' group. Whereas whenever I am talking about C glycosides, because the other groups are hydroxylated, you will see mostly the C glycosylation will happen on 6th and 8th position. These positions generally the hydroxys do not occur. So when I am talking about a C glycoside, it will be mostly there at 6, 8. When I am talking about O glycosides, it will be there at 3, 5, 7, 3' or 4' most commonly. Now how do you extract flavonoids? Flavonoids, like I said, may be mid-polar to polar. So whenever they have sugars attached to it, that is whenever they are in the glycosidal stage, they are more polar. In that case, they can easily be extracted with water or mixture of water and alcohol, that is your hydroalcoholic solution. Whereas whenever you have native flavonoids, the genins or glycones per se, in that case you can use little non-polar solvents ranging from alcohol, ether, ethyl acetate, butanol or even chloroform. Now how do you evaluate or how do you check for the presence of flavonoids? To check the presence of flavonoids, there are few common tests. The first one is your Shinoda test, Then is your alkaline reagent test, lead acetate test and ferric chloride test. So let's discuss them one by one. So Shinoda test is the one of the most common tests which is used. Now Shinoda test is a extension of what you call it as your Clemenson's reduction. In this case, your flavonoids get reduced to anthocyanins in presence of, rather than zinc HCl, you will have your MnHCl. So to get this reaction, what you need to do is you take your plant, extract it in alcohol, take the ethanolic extract of the plant, and to that you will add your magnesium turnings. Be careful, don't add excessive, otherwise those magnesium turnings will make the solution appear much grayish because of the metal. So just add 3 to 4 pieces of magnesium filings and add your concentrated hydrochloric acid. Now interestingly, you will see the reaction happening. The HCl will react with the turnings and hydrogen is released. So you can see the hydrogen gas bubbling out, and in the process the reduction starts. As the reduction proceeds, it might take a little time, like 2 to 3 minutes, and you will see as compared to your extract, your solution now starts turning little pink to red in color. Now if it is an extract, you will observe a very soft color change, but if it is a pure flavonoid, the color change which will be much more intense. So depending upon what compounds are present, you might get a little difference in color. Say for example, if you have flavones, you might get orange to red color. If you have your like flavonoid derivatives, pure form, you will get red to crimson color, and deep magenta if you have a flavonone derivatives. Now if you see your chalcones, or if you see your orone kind of derivatives, they don't clearly answer this test. So for chalcones, what you can do is, there is a test called as antimony pentachloride test. So you take or extract your chalcones, or especially take a alcoholic extract of your chalcones. To that you add your antimony pentachloride and carbon tetrachloride. You will see that gradually a reddish purple color or reddish violet color develops. That indicates that you have your chalcones present in the solution. Now another test is alkaline reagent test. Now this test is something which was discovered by a keen observation. So whenever you take a flavonoid containing test tube and just wash it with your detergent, you will see that the test tube turns bright yellow, and this gave rise to this test, what is called as alkaline reagent test. So if you have your flavonoid or alcoholic extract of flavonoid, and if you treat it with any alkali, especially like your NaOH, you will see that your flavonoid turns bright yellow or yellow orange in color. Now what happens here is your ring C opens up. So if you remember your flavonoids, so now this is what is going to happen. Your ring C opens up, and as a result you get an intense yellow coloration because it forms a sodium salt. And depending also upon the other hydroxys, they will also form metal chelates with sodium salt, and as a result you get a nice yellow shade. Now this shade shows a nice UV absorption maxima, one's between 259 and other between around 362 nanometers. The next test what you can carry out is lead acetate test. Now lead acetate test is a test to see whether a polyhydroxy groups are present in that. So this is true for polyphenolic compounds. So what happens is your lead forms complexes with the polyphenolic groups, it forms chelates, and with flavonoids it forms yellow color chelates. So later on this precipitate out, and a formation of yellow precipitate indicates your flavonoids being present. Another test is a test we also saw in tannins. When you saw condensed tannins, catechin type, they have a good resemblance with your flavonoids in terms of biosynthesis, in terms of structure as well. So they perform or they give the same test as that for the condensed tannins. So the ethanolic extract, if you treat it with 5% ferric chloride, you will get a nice greenish or deep green color complex which indicates the presence of flavonoids. Now how do you quantify? Now If you want to see this, you can do a TLC or you can do a HPTLC to quantify. So TLC is a technique where you have your stationary phase, which is polar silica in our case, and in some cases this silica is coated with a fluorescent dye which is giving you a good fluorescence at UV 254. Now whenever your flavonoids run on this plate on a very polar mobile phase, you will see some bands coming out. So what is going to happen is, because these flavonoids have double bonds, they tend to quench the fluorescence. That means they will tend to pull back the fluorescence. As a result, this will appear black. And what happens here is the remaining plate will show or continue to show a green fluorescence. Now in some cases there are certain reagents which will help to give you a good fluorescence by themselves, but at a little larger wavelength, that is about UV 365 nanometers. One such reagent is often referred to as natural product PEG reagent, which is 1% solution of diphenyl boroxyethylamine. Now this is subsequently treated with PEG, that is polyethylene glycol 4000 grade, and if you see this plate under UV 365, you will see different colors. Now this different colors are also indicative of flavonoids, like epigenin will give you a yellowish green color, your rutin will give you orange color. So not only are they derivatized, their color will also tell you the type of flavonoids. You can non-specifically check these compounds, especially the double bond compounds with iodine vapors. Wherever the double bonds is, the iodine will add up and show you a dark bands. And also you can dip it in ferric chloride, it will give you greenish, blue, blackish color bands. Another ways you can quantify is colorimetry. So they form a good metal complexes. So you can react your flavonoid solution with aluminium chloride. Now they will form a good color complexes which show UV maxima at 415 nanometers. So react it with AlCl3 in presence of like sodium acetate buffer and then quantify it. It will also form color metal complex with different metals attributing to their polyphenolic nature like iron, aluminium, antimony, zinc and so on. Now modern methods use very chemical detection or chemical detectors or even HPTLC, HPLC with a good quantification system like a PDA system, photodiode array system, or a UV vis detector can help you detect the flavonoids. So these are different ways in which you can quantify the flavonoids which are present in plants. So here are few references if you wish to know more about this set of compounds, and thank you everyone for your patient listening.